All right, let's get started. Oh, one sec. So I get my screen share. Just to confirm, I'm not muted, right? Y'all can hear me?
You chilling, yeah.
All right, cool.
Yes.
All right. Yes. All right, cool. Let's get started. So, this Leetcode Friday is going to be basically talking about linked lists, but since we started with the 111 stuff, which is a little bit easier, we're going to just start with something simple like a string. So here's our first question of the day. This is for those of you who are freshmen or who are new to Leetcode. This is a pretty good, easy level solution. So this problem is called length of last word. So just given a string S consisting of words and spaces, return the length of the last word in the string. So if you look over here, we got hello world, right? And world is 1, 2, 3, 4, 5 characters long. It's the last word in the string. You return 5. Right? Fly me to the moon over here in this problem. Right? Notice that we have spaces here, but that's okay. We have the last word is moon, and we're returning 4 characters. And over here, Luffy is still Joy Boy. I don't know if this is supposed to be like a spoiler for One Piece because I haven't seen One Piece, but I'm guessing this is about One Piece. Joy Boy, last word, right? 6 letters. This would return 6. All right, so this is all the questions trying to ask you to do. This is a really, really simple problem. So all we're gonna do is we're gonna iterate through the string, backwards. So, say we have, let me erase all of this. I guess we can do from hello world. Or let's do fly me to the moon because it makes more sense, right? So we're gonna start with this as this problem. We're gonna start from the end of the string, which you can do pretty simply by, for example, just getting like the length of the string, right? -1. That normally would give you some number that is the last index of the string, right? So we want to go to the last index, and we're gonna have a variable. We can call it, I guess, length, right? And we can go through the string backwards. So we're gonna go one by one, backwards, right? Until we hit our first character. So we're gonna ignore this space. And until we find our first character, we're gonna start adding stuff to our length. So now length would be 1. Then we can go here, length would be 2. Here, length would be 3. Here, length would be 4. And then we reach this empty space. Once we've reached an empty space and we've started counting the length of the string, we can just, that means we're done, just return this length. So it's a pretty simple solution pretty quickly, again, just to kind of summarize what we just did, because this is a very quick solution. All we're doing is we're starting from the last part of the string. We're going to just ignore any spaces that they're at the end. And the second that we see a character that's any letter, right, that's not a space, we're going to start counting. And once we start counting, we're going to keep counting. And once we reach the next space, that means that the word is done. We can return the length of the word. And this would be, length would be 4. All right? Any questions on this one so far? No? All right, let me hop back on. We'll code it out. All right, cool. All right, length of last word. So we're going to have 2 different variables here. I guess we can call this first variable p for pointer, right? And then length. So we can do first one could be length of your string, and your length would be 0. So pointer p would be length string, length would be 0. And then we're going to go while p is greater than 0, which means that we're still indexing through the string. We haven't gone negative because the first index of hello world would be 0, right? Anything to the left of hello world would be negatives, and we don't have negatives in the string. Okay, and here we could just start with just removing 1 from p because we are 0 indexed. So length of s would actually be 1 number higher than the size of the actual string. So we go p, and then over here. So let's say we're somewhere in the middle of the last word. So then if string in location P is not equal to a space, we add length plus equals 1. So that just means over here, in fly me to the moon, right? If any of, because we're going backwards, if any character is not a space, then we start adding stuff. But for now, remember the length is still 0, right? And then the else is, so here is the end of the last word. So else if length is greater than 0, return length. And then just another return length. This should work. Yep, here we go. We're done. So all I did was that first we're going backwards to the string, right? Fly me to the moon. So remember, if length is greater than 0, return length. Length will be 0 forever until we hit the first character. So we're not going to return anything when we're in the first empty space going backwards. We're going to wait. Once we get to our first letter, that's when we start counting. So while it's not an empty space, we're going to keep counting. So 1, 2, 3, 4. Then we get to a space, right? And length is greater than 0. So we return length. And that's how we get to the end of the solution. And this would be big O of n in terms of time complexity, because we could potentially just be one giant word on nothing else. Space complexity would be O of 1, because we're not using any additional space. Any questions on the solution? No? Okay, so let me show you a fun solution. So if you like, so the reason why we talk about why Python is just great for this type of stuff is you can just do this. Return length of s.split dot pop. I think this works. It works. So what we did was in Python, you can also, I'm not sure if this is more efficient. I'm assuming probably not. All you're doing is I'm returning just the length of whatever the last word is, because s.split, so .split is a function in Python, splits this one giant string into multiple strings. I believe it's like a list of strings based off something, usually spaces. And then .pop is just giving you the last element of that array or list. So by splitting this fly me to the moon, it would be fly me to the moon, and then pop's last element is moon. That's another solution. I believe though that the space complexity of this would be O of n, because you're making a new list. So just a fun little aside. You can just do this in one line of code. All right. All right. So no questions on this one. Let's move into the linked list now. So I'm just quickly take a screenshot on my iPad and I'll hop over to the other screen. All right. Cool. All right, linked lists. So hopefully if you are, this is like your first time trying a new type of data structure, it's not like an array, you might be a little bit confused as to what's going on, because it is a bit more of an abstract data type. We don't actually, it's not just built in to like our language, like in C or C++ or anything, where it's just you have a contiguous list of numbers. For example, here's an array, 0, 1, 2, 3. We're all used to that. It's all pretty simple. Linked lists are a little bit different. So I'll just quickly go over what a linked list is, just in a very overarching idea, but hopefully this gives you sort of an idea of what we're doing. So linked lists are a more abstract data type, data structure, where instead of just having an array, right, where we have 0, 1, 2, 3, and it's just all in one giant block, we kind of decide to have pointers instead. So this picture over here that we have kind of is pretty much what it is. So in a singly linked list, we have, say, our first node, and say that this node is going to be 0, right? And here's a big circle. So this is our node. This node is going to have it's going to be a value, and it's going to have a pointer. And this pointer is going to be pointing to the next, I'll do squares, to the next block of memory that you want to have. So say this is 1, right? We split it. We're going to have this one pointing to 2. And then this could be pointing to null or something to end the linked list. So all we're doing is that we are linking these nodes, right, to each other to create sort of a list. And the benefit of having a linked list is that certain things such as removing the first element, right, removing the last element, it's very easy to do. Because if I wanted to make, for example, this 1 be the first element in the array, all I have to do is, if this is the head, I can just say that this is head, and then this is gone. We're done. Everything else stays the same. The whole list stays the same, so this is an O1 operation. If we try to remove the first element of an array, though, this would be a little bit more problematic. So if we remove the first element of the array, we'd have to move everything back by 1. So this would create our array of 1, 2, 3. And this would be an O of n operation to remove first. And this would be O of 1 in the linked list. Likewise, if you have, let me show another example. You can also have a doubly linked list, which you'll learn about this in 3.13 if you haven't yet. It's a little bit more handy. So a doubly linked list is, you can think of it sort of like this. You can call it like a dummy node. This is just kind of like your home base, right? You can call it your head and your tail, whatever. But you can have a next pointer and a previous pointer. So when you have, say, 0 as your first value, it's going to point to the previous node and to the next node. So we'd be able to kind of go through this list, previous and next, which helps us traverse it and kind of walk around and do more stuff with it. This is really helpful for doing stuff like stacks or queues or double-ended queues, which are more advanced data structures. It's easy because you can just remove and append from the last or the first very, very easily at that point. So yeah, that's kind of like the basic of a linked list. I'm not trying to go too deep into it because hopefully you already know what they are. And you've hopefully done a little bit of experimenting with them in your classes. I know you learned them in 2.12, and you're definitely going to learn them in 3.13. All right, so reverse a linked list. Here, given the head of a singly linked list, reverse the list and return the reversed list. All right, so this is pretty simple. All we're doing is we're trying to turn this list, right? 1, 2, 3, 4, 5. We're trying to reverse these pointers. We're trying to reverse it. So instead of saying 1, 2, 3, 4, 5 in this order, right? We're just reversing it. So it'd be 5 to 4 to 3, 2 to 1. All right. So this is going to use a strategy that we learned a couple weeks ago. It's called 2 pointers. We're going to have 2 different pointers pointing to the list to kind of figure out where we are and swap these little arrows around. So first off, say we have 1 over here, 2. Actually, let me just erase this. I have more space down here. 1, pointing to 2, pointing to 3, and then this is just pointing to nothing, null. All right, and we want to reverse this so it becomes 3, pointing to 2, pointing to 1. All right, that's our goal. So what we're going to do first is we're going to have 2 pointers. We're going to have a previous pointer and a current pointer. Okay? We're going to start our previous over here and pointing to nothing, null. And we're going to have our current pointer over here. Okay? So now what we're going to do is for each one of these nodes, we're going to set their next pointer to the previous. And we're also gonna save this point. We're gonna save this node over here so we don't lose it, right? Set this to next, and we're gonna save this into like some sort of like a temp node. You can think of like a dummy node, just to remember where it is, right? Then we're going to move on, and here's our current. And now our previous node. Is over here. Okay, and then same thing again. We're going to set our next pointer. We're going to save this. Make sure we save it though, because if we just throw away a next pointer, this is going to be lost forever. So we want to save this next pointer, and then put this next pointer pointing over here. So you're reversing it one by one, and then just move the previous and the current one up all the way until we get to the end. So all we're doing is we're iterating through the array, through the linked list. We're swapping the pointers around, kind of using 3 pointers almost really. And that should, in essence, reverse our linked list. So over time, after doing all of this iteration through that list, the pointer should end up being like this. And then the last one is null. All right. It'll make a little bit more sense when we code it out, but this is sort of the general idea. Any questions so far? No questions? All right. All right. So here we go. So we're going to have 2 pointers. First point is going to be current, and that's going to be just pointing to our head. So right now, if we look at this image, right, the 1 from 1, 2, 3, 4, 5, that's going to be our current pointer. And our previous pointer is going to be null. So while this current pointer exists, which means we're going to iterate through the entire linked list. And remember, the next after the last would be null. So while current exists, we're gonna do a pointer called next, and call it, and just save it. So it's gonna be current.next. So what we're doing is say if we're at 1, right? We're putting a pointer. We're saving the pointer going to number 2. We're just saving that in a variable. And now current.next equals previous. So what we did is we just reversed that arrow. So that arrow going from 1 to 2, it's pointing out to previous, which if we look for here would currently be null. And then previous is equal to current, which just means that now we're moving the pointer 1 up. So previous was the null, so now previous would be at 1, and then current would be next. So what we just did was the current was at 1, we just hopped it over to 2. So we had essentially reversed the first next pointer. So 1 is now pointed to null, right? And now we're at 2. 1 is previous, 2 is current. And then we just repeat that over and over until we get to the end of the list. And in the end, we just return previous, because the current would be pointing at null at the end of the list at 5, and prev would be stuck at number 5 itself. So 5 is now the head of the list, and it's going to be pointing 5, 4, 3, 2, 1, and you just return it. And if you run it, that's it. You're good to go. So this is going to be big O of n in terms of time complexity, because we are iterating through the list once. Space complexity, I'm not too fully sure. I think this would be O of 1. We're not really making it. Yeah, we're not really making a new list. We are adding a pointer, but like that's not really anything else. So this would be O of 1. So yeah, that is reversing a linked list. Any questions on reversing linked lists? Any questions on linked lists at all? Okay, so let's do the next one. Merge 2 sorted lists. Let me just screenshot this and put this on the iPad. One sec. All right, let me swap over. All right, here we go. So merge two sorted lists. You are given the heads of two sorted lists, linked list 1 and list 2. You want to merge the two lists into one big sorted list. And this list should be made by putting together the nodes of the first two lists. What that means is that you don't want to just you want to use as little space as you can. You only want to have constant time space. O of n space, because I'm sure you can probably hack your way around doing with other stuff. All right, so the solution for this one is also similar with pointers. Let me draw out the list over here. So say we have list 1, and it's going to go 1, 2, and then say 4. Right? List 2, going 1, 3, 4, 5, 6. All right, and our output is going to be over here. All right. So this specific problem is very simple. If you think about it, it's just as iterating, because they're sorted. If they were not sorted, this would be kind of a big pain in the butt. But they're sorted. So all you have to really do is just compare each thing one by one iteratively until you get to the end of the list. So let's start over here. So let me just do it. First of all, with linked list, it's usually helpful to have sort of like a dummy node, or like a sentinel node is what they call it sometimes as well in some classes. So we can call it sentinel. So that's just like an empty node that has nothing there, but it's just meant to kind of be the head. So no matter what, you will never lose this node. Like, this is always going to be there. It's your best friend. It's never going to leave you alone, and you're also just not going to know he's there. So sentinel is there just for linked list purposes. And here we're going to have our first output. All right, so let's compare list 1 versus list 2. Is this greater than this? No, they're equal. Okay, so let's just do arbitrarily, just choose list 1. So this is the first node. I'm going to go over here, put that there. Okay? All right, so now we've checked the first one in list 1. Now we're here. Okay, and we're here in list 2. So compare. Is 2 greater than 1? No. So we're going to use this one. So then we're going to add this to our list. 1, 1. Cool. So since we use list 2, let's move our pointer up by 1. All right, here we go. All right, let's compare. Which is bigger, 2 or 3? Sorry, which is small, 2 or 3? 2 is smaller. So that's going to be our next number on the list. Cool, and since we use list 1, let's move the pointer up. And now we're here. Okay. So now we're on the next part of the list. 3, right, is smaller than 4. So we're going to use 3 as our next number. Okay. And now we're going to move that pointer up by 1. All right, and since we've been if they're equal, we've just been kind of using list 1 just arbitrarily. So let's do that. 4. And now, oh no, we're pointing at null. We have completed list 1. All right, so then after we have iterated to at least one list, the rest of the list is going to be sorted. So list 2, we can know that everything else in list 2 is either going to be greater than or equal to 4. So it's going to just be added out to the end of our output list. And the cool thing about linked list is that you don't have to copy this node 5 and then this node 6 to create all of this type of stuff. Instead, what you can just do is grab this pointer and just point it over here instead. So so we don't even have to change anything. We just point to the end of this list. So in the end, this would just kind of move it over here. And we have our list. So that should be our output. All right. Any questions on the iterative approach that we're taking for this merging two sorted lists? No? Okay. Moving on. All right, let's code it. So, like we talked about before, it's always nice to have sort of a sentinel or a dummy node. We just can be an empty list node. So over here, as you can see, it gives you the definition for a singly linked list. The list node has a value and a next pointer. So we're just gonna give it a good old, just nothing in there. All right. And then tail is going to be sentinel. So what we're doing is our tail is going to be sort of like the tail of our output list. So like the current last number of our output list. All right. So here we go. So while list one and list two, what this is saying is while list one and list two are both not null, aka we're still pointing to a current node of both lists at the exact same time, right? We're going to be in this loop. So if list one that value is less than list two that value, what we're doing is just we're comparing the two values of the current list one, list two. So if we're looking at this picture on the left, it's 1 and 1, right? We're gonna say tail.next, actually not now, tail.next is equal to list one. So what we're doing is that the current tail of our output is going to be pointing to the current first node list one. All right, and then list one is equal to list one.next. So what we're doing is that now the tail is pointing to the one in the first list, right? And then the current list one pointer is pointing at two now. So we're moving one in the list. All right, else tail.next is equal to list two. We're just doing the opposite. Nothing different. List two equals list two.next. Okay, and these are our two conditions. And then regardless of which one is bigger, we want to move to the next in our next node in our output. Okay, and then this is practically it for while both lists exists. Now, if list one still exists, aka we've exhausted everything in list two was smaller, there's less numbers in list one or something like that, then we just want to add list one to the rest of our list. Else, if list two exists, right, and list one doesn't, tail.next is equal to list two. And that should be it. Just return. So now, instead of returning sentinel, which should be like our list, we just say sentinel.next, because our little dummy node is just hanging there. He's our best friend. We always know that our dummy node or sentinel.next is going to be the beginning of our linked list. So if we run it, it works. And there we go. So we just merge this over here, 1, 2, 4, 1, 3, 4. It combined them, and now we have our output. So this is actually going to be the exact same thing we do for the next one, which is merge case order list, which is Leetcode hard, but this is part of that algorithm. So this would be time complexity would be big O of n, because we're iterating through the list, both lists in total. I guess you could say n plus m if you really want to be pedantic, right? With length of n being the first list and n being the second list. And then space complexity would be O of 1, I believe, because you're not making anything new, you're just moving the pointers around. So you're not creating anything new, you're just kind of shuffling things around. All right. Any questions? Or any comments, concerns? Nope. All right. Let's do merge case sorted list. The next one is supposed to be remove Nth Node, but merge case sorted list just kind of works out because it's literally the same thing but just more. And the cool thing is going to be actually this is our first Leetcode hard of Leetcode Friday, so this is going to be a little doozy. This took me a while to figure out, but it's actually pretty fun. It's a pretty fun algorithm. So just copy this over to my iPad. All right, let me share my screen. All right, kids, this is going to be your first big boy Leetcode problem. A Leetcode hard. Hey, right. Okay. Oopsie. All right, so here we go. Merge k sorted list. You're given an array of k linked lists called lists. Each linked list is sorted in ascending order. Merge all the linked lists into one sorted linked list and return it. All right. So what this is just saying is it wants you to it's the same thing as before, where you instead of merging two sorted linked lists, you're merging a certain amount of linked lists, which are all sorted, which could be 2, 3, 4, 500, doesn't really matter. So we're gonna be doing sort of like a more general algorithm of merging linked lists. All right, so for this one, this is a bit of a doozy. Hold on a second. Let me just look at my notes. All right, so for this one, we say here's our first example. List is 1, 4, 5, right? 1, 3, 4, 2, 6. So 1, 4, 5, 5. Actually, let me move this somewhere a little bit easier to read. 1, 4, 5. Okay. Or actually, let me just do an even easier example. Let's just do 4 linked lists of linked 1. 5, 7, 3, 8. Here we go. All right. So here we have 4 different linked lists, and let's just pretend that they only have one variable because that'll be a little bit easier. What we can do is actually an algorithm that's sort of like merge sort. So we're going to divide and conquer with this problem. What we're going to do is we're going to compare these two and compare these two. And we're going to divide and conquer this problem to make it a little bit easier. So 5 and 7, right? 5 is less than 7. So we're going to merge these two lists, right? And here's our first list. 5 to 7. These two become this one list. And let's merge this. Should be 3 going to 8. Okay? So now we have 2 lists, right? And now we have 2 unique lists that are both sorted in ascending order. And this is exactly like the last problem that we just did. So now we just need to merge these 2 lists, which would be 3. Compare this, right? 3, then 5, and then 7, then 8. All right. So all we're doing in this specific problem is that we are going through these lists, and we're just going to divide them and conquer them. We're going to split the problem in half, right? So if we have 4 lists right now at the beginning, let's merge the first half with the second half, and merge these two, split it from 4 lists into 2 lists. So now we've cut our problem in half. And now merge these 2 lists into 1 list, which is cutting our problem in half again. 7 to 8. Right? So this is sort of like a variation of merge sort, but just in terms of we're dividing and conquering. So now, if you think about it, we have k-link lists. So k-link lists, and we have say m, or can we say m?
In this case,
Yeah, we can say like m. We have m elements, or yeah, m subproblems. I'm trying to remember like off the top of my head because I did this a while ago, and I'm kind of having a brain fart. But I know that the overall time complexity would be O of k times, I guess you could say like m log m. I forget because I just know that merge is n log m or m log m, and it's k times because you have k linked lists. Yeah, I don't know why I'm having a brain fart. Anyways, any problems about this conceptual idea of merging k-sorted lists? All we're doing is we're dividing and conquering, until we get to have 2 linked lists, where we just do the basic good old merge 2 linked lists together. Any questions? It'll make a little bit more sense once we code it up, because it's a long one. No questions? All right, let's code it up. All right, so we're gonna start off by remembering we just talked about how we're gonna be merging 2 linked lists, right? So let's just remind ourselves here. We're gonna have a helper function. Merge 2 linked lists. So let's just do this out of the way. It's the same exact thing as this merge 2 list thing, but I'll just type it over again. All right. We'll do a little merge list and self just because this is class list 1, list 2. All right. Just for now, so it doesn't give us red stuff. All right. So same as before. Right, we have a dummy node is equal to list node. Tails equal to dummy. This is literally the exact same thing as before. We're just going to do this helper function to kind of recursively, or not really recursively, but just merge two lists together. So while list 1 and list 2, exact same problem as before. If list 1 val is less than list 2 val, tail.next is equal to list 1. List 1 is equal to list 1 next. Again, this is the same thing as before. Else tail.next is equal to list 2. List 2 is equal to list 2 next. And then we had tail equals tail.next. And then we had if list 1 tail.next is equal to list 1. If list 2 tail.next is equal to list 2. Return dummy.next. All right, I believe, oh, misspell. Next, there we go. So this is the exact same thing as our last function, merge two sorted lists. So it's literally the exact same thing, but instead of dummy, we call it sentinel. We're going to be using this. This is a little helper function, and this is something that's really good to know. Whenever you're doing harder LeetCode problems, don't feel afraid to add multiple functions in your solution to kind of abstract things away, because if you had to do this in the main code, that's just going to be super confusing, and you're going to get lost. So split up the problem. You know you're going to be merging two linked lists eventually, right? So just have helper function in there. All right, so now let's get started to the actual merging k-lists. All right, so if not lists, so if no list exists, or the length of lists is equal to 0, return none. What this is saying is that if we have no list at all, so in the edge case that the list is completely empty, or at the point that we have exhausted all our lists, right, just return none. This is an edge case. All right. So while the length of lists is greater than 1, because again, we are getting a list of list nodes, or a list of linked lists. So while we have some number of lists, so while we still have lists to merge together, we're going to create a merged lists list, or array, you could say. Lots of lists going on in this problem. So we're going to have an array called merged lists. So now here, for I in range, we're going to go from 0 to the length of lists, and we're going to hop by 2. So what we're doing is we're going through this array of linked lists, and we're going to go in pairs of 2, because we're going to merge these in pairs of 2 to make this problem a little bit easier. So list 1 is equal to lists I, so we're in the current spot, right? List 2 is equal to lists I plus 1. But what if we're at the end of the list of the array of linked lists? This could be a null pointer, and that could give us a error because we're out of bounds. So we can say if I plus 1 is less than length of lists, else just return none. So it's either if I plus 1 exists, then we're going to merge list 1 with list 2. If it doesn't exist, then we're just going to merge list 1. So we're going to append merged list dot append ourself that merged list 1 list 2. So what we're doing over here is we are appending to our new empty array of just this giant merged list. We're gonna merge the current list 1 and list 2. So what we're doing is we're iterating this list to list, and we're doing it in pairs of 2, merging them and adding them to one big list. All right. And afterwards, lists is equal to merged lists. So this is just kind of like a temporary variable. So that way the actual list, the original list input is now this merged list. All right, and then we return lists 0. So what we're doing is we're returning the first list and the only list that's in lists. So I think this is okay if I run it. Let's see if it works. I'm crossing my finger. It works. Cool. If I submit it, here we go. Perfect. So again, just to summarize, we merged k-sorted lists. So what we did was we broke out the problem, right? We we broke it down into sort of like a divide and conquer algorithm where we're gonna break it up into pairs of divide the problem in half each time. So we have 4 lists, we dropped it down 2 lists and 2 lists, and then we combine those to be just 1 list, and 1 list combine those to be 1 giant list. This is a divide and conquer algorithm, which would be again n log n for that merging, and then times k lists. So this would time complexity would be big O of k times, I guess, n log n. Space complexity, I would have to double check. I think that this would just be O of n, or k times O of k. I'm not too sure. I have to double check. I'm not going to give you that correct answer because I don't want to lie to you. But the complexity is k n log n. All right. Any questions on merge k sorted lists? No, this is a Leetcode hard. So if you have any questions at all, let me know. We're just building on from the last problem.
Why do you even have any space for space complexity? Shouldn't it be constant?
Probably is constant. I get it. I'm not really good at analyzing these space complexity for list problems yet, so I don't want to like lie and give a wrong answer. But it does seem like it
Space
could be of
complexity for
one
merge list, the original problem.
for the original problem. It would be O of 1.
Okay, and then
Yeah. So
what else are you doing on top of that? So in your main function.
because we have merged list over here, so we're adding like 1. But I guess it would be just technically still O of 1 because we're not really making anything new, right? We're just kind of moving things around.
Yeah.
Yeah. So yeah, I think it is O of 1. Either way, like yeah, it doesn't feel like it's too big of a space usage. All right, next problem. Thanks for your help, Clint. All right, remove the nth node from end of list. All right, let me just add this to my iPad and we'll do the last problem. But again, does anyone have any questions about these so far? Because we are doing some pretty hard ones now. If you can do case ordered lists, you should be good for most interviews for internships at least. All right. No questions? And then let's do the last one. Remove nth node from end of list. All right. Okay. So given the head of a linked list, let me zoom up for a little bit better. Given the head of a linked list, remove the nth node from the end of the list and return its head. So say we have this list over here. It says 1, 2, 3, 4, 5, right? It's length of 5. And we want to remove n equals 2. So it's 2 from the end. So this is 1, 1, and this is 2, right? So we want to just delete this and just make this 1, 2, 3, 5. So this would be a lot easier if we were just doing it from the beginning. So it's like remove the 4th node of your linked list. That's really easy because all you'd have to do is just traverse your way through the linked list one by one. Bing, bong, bing, bong. All right, we're at number 4. Great. Let's do this 3-pointer. Make it 5. Done. Easy peasy. Lemon squeezy. Oh, Ben. No problem. We're done. But since we're going in reverse order, and this is a singly linked list, we don't actually have we don't have a tail pointer. We don't know what the last number of the list is. This is just pointing to null. So we have no clue of figuring out like what's going on, which makes it a lot harder. If this was a doubly linked list, then you can just go from if this could be like a tail, right? And then you just go from there and easy peasy. But we can't. So what we're going to do instead is we're going to do our good old-fashioned 2 pointers technique because 2 pointers is really, really good for traversing lists. Let me draw it out for you guys, and I'll show you how it works. All right. So we have list 1, 2, 3, 4, 5. And then let me just move this a little bit more to the left. And then null. right? Okay, so first of all, let's just add a dummy node because this will make the problem easier. And we're going to have it over here. Okay, so what we're going to do, first let me show you the intuition behind this. Okay, so we're going to have 2 pointers, a right pointer and a left pointer. And we're going to say if n equals 2. Okay? We're going to have the pointers two apart. So 1, 2. Okay? So what we're doing, or is this, hold on, let me just double check this is correct. Oh no, yeah, this is right. Yeah, so this is left pointer, this is right pointer. Okay? So what we want to do is we want to kind of traverse over here, left and right. And then keep going. And then this would be right. This would be left. But we still don't know that this is the last number until we get to null. So now right is over here, and we hit null. And then left is over here, right? And then we want to delete this. So this is 2, right? Because we have a spacing of 2, n equals 2. We're spacing left and right pointer between each other. Once we hit null, we know we're at the end of the list. We want to delete the number the left pointer is at. So we want to delete this and say bye-bye and route 3 to 5. But again, this is a singly linked list. We can't go backwards in a singly linked list. So we technically actually want to go one more back than that. We actually want to be at number 3 when we're doing this in order to be able to move 3's pointer to 5. So the way we can do that is by using a dummy node, just because it makes things a little bit easier for us. So instead of starting, instead of starting from over here, right, left and right, we're actually going to scooch left over one more and have it over here, left. By doing that, it just means that we're able to kind of move things around, and once we land to that null pointer, we're going to be done over here at the 3, which means that we can move that pointer over here, delete that by just going yoink and pointing to that 5. All right, and that's sort of the intuition behind this algorithm. So by doing this, we're only traversing the list once, which means that our time complexity is O of n, and our space complexity is O of 1 because we're not using any additional space. We're just constantly going through the list. All right. Any questions on the drawing of this problem? No questions? All right. Let's hop over to the code. So this was remove nth node from n list. All right, cool. Here we go. So let's start again by having a dummy node. List node 0 head. So what we're doing is we are creating. So again, over here, if you look the values for a list node class, we initialize it with the value and the next pointer. So first argument is value, second argument is next. So we're creating a dummy node with a value of 0, just because we don't really care. And then the next pointer is pointing to the head. So we're creating a dummy node before the linked list. This is now going to be officially like the first item of the list. So then we're going to have left pointer called to the dummy node, and then right pointer to the head. Okay? So then while n is greater than 0, because again, we're given a number n, and we want to have that n amount of space between things. So while n is greater than 0, we're going to just move the right pointer. Right equals right that next, n minus equals 1. So what we're doing over here is we're scooching over the right pointer one by one until we hit n spaces between the 2 pointers. All right, so it'd be n numbers afterwards. So if n was 2 and the right started at the 1 of this picture, 2 number after would be at the number 3, and then the left is already initialized at the dummy node. So we have moved our pointers are good to go. Let's start the algorithm. So then while right pointer exists, aka while right pointer is not null, we are not at the end of the list, left is equal to left.next, right is equal to right.next. So all we're doing is we're scooching over the pointers one by one, traversing the list, right, until we get to the end of the list. This is just good old list traversal. And then we're going to delete So now left.next. Once that means by the time we're here, by the way, by the time we get to this point in the code, we have officially reached the end of the list. We are at the point where if we were at the 3, we want to delete 4. So we're there. Left pointer is at 3, the right pointer is at 5. We're there. So left.next is equal to left.next.next. So here's where we're saying 2 next over. So 3, the next one would be 4. But what we're saying is that 3 is actually going to be the pointer pointing from 4 to 5. So we're pointing the arrow now from 3 to 5. And that's and then afterwards you just return it. Return dummy.next. And I believe that this is good to go. Yep, there we go. We're done. So we run it. Again.
Sorry, there is not.
My Siri spoke up. So there we go. This is a O of n for time, because we're iterating through the list once. O of 1 for space. Right. Any questions for remove nth from end of list?
Just to reiterate, so with your n, you use that only for your right pointer to go after your nth node, and then left will just is just there to sort of move around it. Because I get it, so it's like because once it's over the nth pointer, you can point your left to your right, essentially skipping that one node. Is that what you were getting at? Because I couldn't solve this one personally.
Yeah.
I kept putting
So
this in a for loop.
yeah. So let me go back to my iPad to draw it out for you. That's a good question. Yeah, you don't have to use a for loop. You could kind of use a for loop, but honestly, for linked lists and any like traversal problems, I personally find it easier to use a while loop, just because it makes me kind of think my thoughts out a little bit better. All right, so here's what we're doing, right? We have our left pointer initialize a dummy, right? And our right pointer initialize at the head, which is technically 1, okay? And our n is equal to 2, okay? So what we're going to do is we're going to, while n is greater than 0, we're going to be doing this. So we're going to move right 1, and now n is equal to 1 because we subtract it. So n is 2, we're doing n, every time we move the pointer is n minus equals 1, we're just subtracting 1 from n. Alright? And then, since n is still greater than 0, we can move the right pointer one more time, and then here n is equal to 0, here's right, and now we have n, right? We have n spaces between, and now we're good to go. Right is in the right position, and then we could do our traversal, which we were talking about before. So left is over here. We move them together at the same time. They're hanging out, they're best friends. So here goes 1, right, from dummy to 4. They move the 1 over here, move 1 over here, and we're going to keep going until right is not null. Sorry, until right is null. So once we hit here, we're at null, we're done with the list. We have officially reached our nth node over here. Right, so this is our node, our left pointer is here. So now we're just saying bye to this pointer and just writing it over here by saying currently it's like left.next because we want to find the next pointer of the next pointer. Our next pointer right now is here, and we want to have that next pointer of this pointer. So we're just kind of doing that. It's a weird syntax, but that's kind of just how it works.
No, I get it, because ultimately you're returning left, not right, right? It's just to help you sort of navigate until you hit that nth point.
Yes, that way you don't have, because remember you can't go backwards, so you don't know when the list is ending. So you're keeping that space of n between your left and your right pointer, so that way by the time you're done with the list, you are officially n spaces away. You know that the next node is the nth node that they want you to delete from the end.
Thank you.
Does that make sense?
Yeah, no, for sure.
Any other questions? Yeah. Any other questions? None at all? Any other questions at all for any of these problems that we just did? Or just any linked list questions in general?
General question, because when going through this one right here, since like I said, I struggle with this one a little bit. I tried making a sort of like a dummy list, if you will, like the same approach as you did with the last one, where you just traverse through it and you only push the ones that you want into that list. Do you think you could do that, or would that just like inefficient to do so?
So, I'll tell you a story. When I first started doing linked list problems, I had no clue how to traverse them, or like figure these problems out. So what I used to do was I would iterate through the entire linked list, turn it into an array. So for each value of the linked list, I just add it to some array. So it'd be like an array of 1, 2, 3, 4, 5. And then I would find that nth element, I'll just delete it from the array, and then turn this array back into a linked list. So I did that when I first, like, before, like, I knew about, like, just better traversal methods. So you can do whatever you want, build new lists, do whatever. That would be inefficient because you're adding way more space and you're adding way more time to it. So what we're in this example that we just did, we were able to traverse the entire list once. We didn't have to do anything new. We didn't have to build anything new. We're just pointing at stuff, which means that we don't waste any space at all. So your idea of making like a new list, it would work, but it would be less efficient in terms of space complexity and potentially time complexity as well.
What's a good cue to understand? Because the difference between like making just a whole new list and realizing I don't have to do that. I can just sort of work with the current list and just make like 2 pointers.
Yeah, that's a good question. Honestly, the best way I can like help you with that is just practice because you're gonna find out that lots of these problems have very similar sort of strategies that when you first try them, you're not gonna come out like from your first shot. If you don't know about 2 pointers, you're not gonna just magically come up with the idea of 2 pointers. Eventually it's just gonna become second nature where you kind of realize, oh hey, I could probably have 2 pointers for this problem because it would make sense since I'm trying to kind of remove a node and I don't know how to get to the end of the list. I have to somehow have to find out where we are. It just kind of comes with practice, but in general, 2 pointers, just for like a general tip, lots of linked list problems can be solved with 2 pointers. We did that with this one. We did it 2 pointers with reversing the linked list. We used the previous and the current. Merging 2 lists, we had 2 different pointers technically pointed to the current first of each list. Case sorted list, we had 2 pointers for merging them again. So in general, I think that 2 pointers is a very common technique that you would use in linked list problems. So it's sort of like when you have like lots of random array or string questions or like count this or count that, you kind of just think, can I use a hash map in this problem? It's sort of the same thing with linked list. Can I use 2 pointers in this problem? Once you understand the algorithm, the idea, it'll just kind of come to you with practice. Any other questions? No? All right, so that's pretty much it for today's Leetcode Friday. Next week, we are going to be doing trees. So we're kind of just going through the roadmap of just like complexity of things like started from arrays, we did 2 pointers, we did binary search, we did sliding window, we did linked lists. Once you understand linked lists and just pointing with 2 different nodes, trees are just kind of like an extension of that, and we're going to go from there. So next week are trees, and then we're going to go, I guess, to heaps, graphs, and all the other fun stuff. All right, guys, so that's pretty much it for today. Have a wonderful Friday, and I'll see you all next Friday.